So movement of gases, and how do they move? They move randomly, right? Move in straight lines till they hit something and they bounce. Okay? So that's going to cause diffusion. Okay? And diffusion is molecules moving from areas of high concentration to low concentration. Spent a lot of time talking about diffusion in biology last year as things diffused across the cell membranes, osmotic pressure, all those pieces. Okay? Well, now we're talking about it with gases. Same idea. Here's an example. Perfume molecules spreading across the room. Closely related to diffusion is effusion. Diffusion happens in an open spot. Effusion happens through a tiny hole. And it's still going to go from high concentration to low concentration. So let's think about what happens when you poke a hole in a balloon. We'll say it pops. It doesn't always pop. But if you poke a hole in a balloon, you got a balloon, there's my little hole right here. Why does the balloon go flat when you poke a hole in it? We want to talk about high pressure and all things, but if you talk about you want to talk about there's more pressure inside than outside, it's being squeezed out, but that's not really what's happening. What's really happening is the molecules in here start bouncing around, and if they hit the hole, they go out. What you probably don't think about is there's molecules out here. If they hit the hole, they go in. So at the same time air is coming out of your balloon, air's going in. It's just going out faster than it's coming in because that pressure, higher pressure, means you're hitting more often on the inside. So the more often you hit, the more likely you are to go out, right? Does that make sense? So faster molecules are going to escape faster because they got a better chance of hitting the hole. Just because they're bouncing around. That's what happens when you poke a hole in a balloon. It's not air rushing out, it's air bouncing around, and if it hits the hole, it goes out. If it doesn't hit the hole, it doesn't go out. And the outside air, if it hits the hole, goes in. So these only depend on how fast the molecule is moving. If I want something to diffuse faster, heat it up. Okay? It'll diffuse faster. But now, let's talk about that second question on the bell work. What the heck did that have to do with anything? Which had more energy? A big rig truck or a car? Okay. You say, well, which one, if your car got hit by one of those, which would cause more damage? The big rig, right? You got your choice between being hit by a car or hit by a big rig, choose the car. Right? But we make an assumption there. The assumption is that the two are moving the same speed. Okay? Because you could have a car hit just as much as the semi. If the semi's going slow and the car's going fast. Right? So to have the same kinetic energy, the car and the semi would not be moving the same speed. Okay? Mass affects kinetic energy. So if you have less mass, you have less kinetic energy at the same speed. So if you've got a particle that's got less mass, in order to have the same kinetic energy, it has to move faster. The car would have to move faster than the truck, right? So that means smaller molecules have to be moving faster than big molecules to have the same kinetic energy. When would molecules have the same kinetic energy? Well, what do we say kinetic energy measures? Temperature. So if you got the same kinetic energy, you got the same temperature. So at the same temperature, smaller molecules are moving faster. And that guides things like perfume design, because you're walking a line with perfume design. You're not putting on perfume so it smells good across the room. You don't want it to move too far. So you want a pretty heavy molecule. But the heavier the molecule, the more electrons it has, the more attractive forces it has, the less likely it is to be a gas. So see how I got two competing interests. I want it to be big and heavy so it stays near me. But if I make it big and heavy, it never evaporates and never leaves me. So it's kind of the dilemmas they have along the way. So everybody comfortable with that? That the oxygen molecules in this room are moving slower than the nitrogen molecules. Because oxygen weighs 32 grams a mole. Nitrogen weighs 28. The nitrogen's lighter, so it's got to be moving faster. So, now I poked a hole in my balloon. In actuality, balloons have millions of holes. Okay? What it is latex is long strands of long-strandy molecules, all intertwined. And when you stretch it, there's gaps between those strands. And that's why your balloon goes flat, is because the molecules hit the inside. If they hit that hole, they get to go out. But you'll notice that your balloon never goes totally flat. Why is that? Well, because there's molecules on the outside trying to get in. If they hit the hole, they go in. So the helium's leaving and the air's coming in. But the helium, well, if they're just changing like that, why doesn't the balloon stay the same size? Well, because the helium is smaller, so it's moving faster inside the balloon. It's got a better chance of hitting the holes than the slow-moving oxygen and nitrogen on the outside. So the helium leaves a lot faster than the oxygen and nitrogen come in. So your balloon goes flat. Unless you have a Mylar balloon, and the only place those leak is if they haven't melted the seal all the way around the edges and the glue where they filled it up. Because Mylar doesn't have the long strands with the holes in them. So Mylar balloons can last a long time because they don't have any place for it, or they have fewer places for it to diffuse out of. So, to give you a sense of what this means in terms of your balloons going flat, let's see if I can show you this. One more. Should be there.
These two balloons contain different gases. Using high-speed photography,
Actually, low-speed photography.
The time is compressed to about 1/2 hour for each second. We can see the results of diffusion.
That's
Let's
5
see
hours,
why the right
6
balloon
hours.
collapsed first. The silver balls represent the molecules of a heavy gas, and the red balls represent the molecules of a lighter gas. The balloon is modeled by a transparent cylinder with an agitator at one end to keep the molecules moving, and pores at the other end, through which molecules occasionally diffuse. We will set the clock for 10 seconds. Notice some of the molecules escape through the pores. Note the diffusion rate in this trial. We will take several samples and arrive at an average value.
Now we're going to fast forward through them.
Run number 2 gave us a diffusion rate of 6. Rate is 6.
Average came out to be
Let's
6.
find the average diffusion rate for the light molecules. Notice they diffuse at a faster rate. Run number 1 gave us a diffusion rate of 16. The average diffusion rate is about 15 1/2. The two gases are helium and nitrogen. Which is which?
One of those balloons started off filled off with hydrogen, the other one with nitrogen. Which balloon's which? Well, which one's going to escape faster? The light molecules or the heavy molecules? Light. And which ones are lighter? Helium's 4, nitrogen's 28. Yeah. So, the lighter molecules escape faster, the lighter molecules effuse and diffuse faster. Direct or inverse? As the weight of the molecules goes up, what happens to the speed they change? Goes down. So you want to say inverse. It's not quite as inverse as we'd. It's inverse plus. Say, well, what do you mean inverse plus? Inverse plus. The rate of effusion and the rate of diffusion are inversely proportional to the square root of the molar mass. So I got the inverse proportion, but now it's not to just molar mass, it's the square root of the molar mass. Where the heck did square root come into? Where did I get that square root? Well, just want to show you where it came from. It's not a magic square root symbol. Okay? The equation for kinetic energy is 1/2 mv squared. That's the equation for kinetic energy. So the more mass you have, the more kinetic energy you have, the more velocity you have, the faster you're going, the more kinetic energy you have, but twice as fast is 4 times the energy. Okay? M is mass, V is velocity. Those are lowercase. Okay, so where does the square root come out of there? Well, 1/2 mv1 equals 1/2 mv2. Right? Wouldn't 1/2 mv1 equal 1/2 mv2? m2v2? So 1/2 m1v1 equals 1/2 m2v2. Oh, 1/2 m1v1 squared, m2v2 squared. I can cross off the halves. I'm going to gather terms. So I'm going to put the masses on the left and the velocities on the right. So it's m1 stays where it's at, m2 gets moved below. v2 squared stays where it's at, v1 squared goes below. And then you take the square root of both sides, and you get the square root of molar mass 1 and molar mass 2 is v2 over v1. Inverse, flipped over, square root. So it comes just from the equation of kinetic energy. So if you solve for velocities, you're going to take a square root. If you solve for masses, you're going to have to square. Okay. So Graham's law as an equation is this. Effusion rate 1 over effusion rate 2 equals the square root of the molar mass of 2 over the molar mass of 1. Remember I used that big M for molar mass? That means the number's off the periodic table. And the reason why it's true is because velocity 1 over velocity 2 Now, very rarely do we actually measure effusion rates. We usually measure how long it took for it to escape. That's easier to measure, right? Then you turn it into a rate. And you take how much escaped, divide by how long it took, and that gets you a rate. But most often, you time how long it takes. So how are velocity and time related? If I go faster, does it take more time or less time? So time and velocity are inverse. Twice as fast, half as long. That's half as much time, right? So since time and velocity are reversed, time and molar mass are direct. Does that make sense? All I did was say, oh, this has got to be, time is reversed, so times 2 over time 1. So you got to look to see, did they give you a rate or did they give you a time? And it's easy check because if you make a mistake, it's most often that you change the wrong way. You got the lighter molecule taking more time or the heavier molecule escaping faster. You get it upside down. That's the most common mistake. So, in the test, he effused at, no, that's not he, it's helium. Effused at 3.5 moles per minute. How fast would N2 effuse under the same conditions? I lost my ones. Which one is it? 13? Well, they gave me rates. So I know that rate 1 over rate 2 is going to be the square root of the mass of 2 over the square root of the mass of 1. Now, I'm lazy. I don't want to solve for things on the bottom, so I'm going to decide that 1 is N2. So that the rate for N2 equals, well, the rate for hydrogen was 3.5 moles per minute. The square root of the molar mass of 2, well, 2 was helium, right? So that's 4.00 grams. That's the molar mass of helium. Because we decided the helium was to go, 3.5 moles per minute is helium, so the helium's got to go inverse on the top side. Okay? And the other one is nitrogen, and nitrogen is 28.02 grams. So to solve that for rate 2, all I have to do is multiply both sides by 3.5 moles per minute. So, push buttons. Now you could be lazy. 4 divided by 28 equals, then take the square root of that, times 3.5, equals 1.3 moles per minute, because all my other units cancel out. So, does it make sense? Well, nitrogen is heavier, so it should escape slower. I got a smaller number. By the square root of 7th. Okay, because that's the difference between, that's the factor, right? The square root of 7. Okay. H2 effused 2.82 times faster than an unknown gas. What was the molar mass of the unknown gas? Well, I know I'm going to want the square root of the molar mass of, I don't know what it is, but that's got to be over the square root of the mass of H2, right? On the other side, it's going to be the rate for hydrogen over the rate for X. How the heck am I supposed to know that? Well, it says H was 2.82 times faster than the unknown gas, right? So that means 2.82 rates of X equals the rate of hydrogen. So this is the rate of hydrogen, right? 2.82 times the rate of X. So those rates of X go away. I don't even have to know what X's rate was. So now I've got the square root of the molar mass of X over the square root of 2.02 grams equals 2.82. Multiply both sides by the square root of 2.02 grams. And you get the square root of the molar mass of X is, pick up something that does math, 2.82 times 2.02 to the 1/2 power, that's how I do it, equals 4.01 grams. But that's the square root. I want the real molar mass, so I have to square that. And I get 16.1 grams. So all I did was take this sentence and substitute for the rate of H2. Got the rate of H2 in terms of rate X. Make sense? So I did a substitution, and he made my rate X go away, which is what I wanted. It took an unknown gas 89.3 seconds to effuse through a hole. Oxygen effused through the same hole in 60 seconds. what's the molar mass of the gas? So this time they gave me times. So I always pick the unknowns so it's on top. So the molar mass of X is what I'm looking for, because I don't like solving for bottom stuff. It'll work, it's just a pain. And if I get to pick which one I'm going to put on top, I'm going to put the one I'm solving for on top. So I know I want the molar mass of X over the molar mass of oxygen, O2. And I want it in terms of time. So I got to decide, is time direct or inverse? If it's heavier, should it take more time or less time? Heavier is slower. Slower should take more time, right? So heavier, more time, that's direct. So the time for X and the time for O2. So this one's not inverse. Velocities, rates are inverses. Time is direct. Okay? Well, I know 3 of those numbers, right? And all I have to do is multiply both sides by the square root of the mass of O2. I know all those numbers. So the square root of the mass of X is the square root of 32.00 grams times the time for X was 89.3 seconds divided by the time for O2, 60 seconds. Seconds cancel out. So 32 times, oops, got to take the square root of that, to the 0.5 power, times 89.3 divided by 60 is 8.42. And my unit is grams. No, grams to the 1/2 power. So what do you mean grams to the 1/2 power? Well, it's underneath the square root, isn't it? So I need to square that. When I square that, the mass of X is 70.9 grams. Hey, that could be chlorine. Cl2. Okay. And that's that. That's how we figure out how things are going to spread around. Here's a few practice problems. That I get to see on Friday. Do not try to do it in the space provided. So I will be picking up two things on Friday, the next time I see you. That would be the Graham's Law practice, practicing a few of those, and the lab. Apologize.